I suppose here, then for last n minus 1 choices, there are n minus 1 plus n minus I plus 1 cars. They have kind of preferred it here. So by pigeonhole, you will see that that cannot be a parking function. So this condition is necessary, and by induction one can prove that this is indeed sufficient also. So a parking function of length n that satisfies this condition. Now I will introduce this generalization lambda parking function. So let me define it. Lambda is some tuple, lambda 1, lambda 2, so on, lambda n, where these lambdas are in decreasing order. Last one is positive. Fix a lambda, something like this, and we say a sequence, it's a definition, a sequence a1 so on up to an is of positive integers, is a lambda parking function if this, again, di's are its non-decreasing, if it's non-decreasing rearrangement, say b1 less than equal to b2, so on, bn satisfies bi less than equal to lambda n minus I plus 1 for all I. So it's kind of generalizing the concept of parking function, and what we have is, if lambda happens to be equal to this n, n minus 1 and so on, to counting what are all possible lambda parking functions. So let me write that formula. So if I denote lambda n to be set of all lambda parking functions of lambda n, its cardinality is given by this formula, n factorial, allow me to write, determinant of lambda n minus I plus 1 power j minus I plus 1 divided by j minus I plus 1 factorial. So this n by n. You can see that if I is bigger than j plus 1, then this is negative, so that part is 0. So each one of them, I mean, this is a determinant of a special form. This determinant appears in a paper of Steck in probability theory, so that's why sometimes this is called Steck determinant. And this formula was given by Giesel. This paper is 1969, long back, and this formula for counting lambda parking function was given by Giesel in 1996. So, yes. But how I got interested into lambda parking function or Journal parking function? So that's a different story. I'll come to this. You take, say, this point 1, 2, 3 in R3. Take all permutations of this 1, 2, 3. There are 6 of them. Okay, so when you take all the permutations of this and then you join, what do you get? You get a hexagon. Okay, you get a hexagon. And this 1, 2, 3, correspondingly, I can also get an ideal. This is what I can say. I'll say it's a permutahedron. Okay? In general, you take 1, 2, 3 up to n, and you take all the n factorial points in Rn, and you take the convex cell of those n factorial points. That's an n minus 1 dimensional polytope, which goes by the name permutahedron. This is a particular case when n equal to 3. And corresponding to this, we have an ideal. IU is what? Each one of them is there. So I have 3 points x, y, z. So I can take x, y, z, q, and take all the possible permutation. What I'm saying is, here you have 1, 2, 3. You take all possible permutation, maybe 2, 1, 3, and so on and so forth. So this ideal in the polynomial ring A, x, y, z, this ideal is called the corresponding permutahedron ideal. And certainly these objects